All right, so welcome back, guys. Today we'll start where we left yesterday. So this problem is a multiple choice one, I guess. So the statement is that to study the variation of velocity in some motion, the velocity vectors at different times in the given motion are drawn from the same initial point with their lengths proportional to the magnitude. In which of the following cases is the curve joining the final ends of the velocity vectors a circle? Okay, so basically they're talking about some point, and all the velocity velocity vectors at different times of the motion is drawn from the same point. Okay, so basically the vectors are like shifted and they're brought to this particular point, and after that we connect the tips of these vectors, something like this. And this is the curve that they're talking about. Okay. Now this particular curve where we join the tips of the velocity vectors and try to plot it on a graph, this curve is a name and it's called the hodograph. Okay. So it's spelled like this. If you guys want to read more, you can just check out Wikipedia, but it's not that relevant. So moving on. Yeah. So basically we have to try to find out this curve for A, B, C, and D. Okay. So that's the task at hand. So first let's start with projectile motion. Okay, so another thing to keep in mind is that this point can be any point. Okay, this does not have to be the center of the circle. Okay, so that could be a very confusing part. So for example, a lot of you may start with the thought that, okay, so if it needs to be a circle, then each of the velocity vectors need to have a constant magnitude, right? And then the tip would form a circle. But the thing is, there's no, they never mentioned that this particular point has to be the center of the circle. This particular point can be any point. Just for the sake of an example, let's just say that point is somewhere over here. Okay, and the vectors are drawn like this. So in this case also, if you join the vectors, you still get a circle, right? But the point is lying outside the circle. So it's not necessary that the point that they're talking about, from where the velocity vectors are drawn, has to be the center of the circle. It's not mentioned, right? So first let's start by defining an origin. So a special point where the tails of the velocity vectors lies. So I'm just saying that is the origin of our coordinate system. Okay. Okay. So now let's just draw an arbitrary vector, an arbitrary velocity vector, something like this. So if this is the velocity vector, then of course I can resolve it into two components, right? Vx and Vy. So the coordinate of this point is going to be Vx comma Vy. So we are trying to plot Vy versus Vx curve, right? Okay, so basically the task now is figure out all the Vy, Vx points, okay, and try to check if they form a circle or not. So we just have to find what is the relation, what is the equation of Vy versus Vx, okay, Vy versus Vx. So this is what we have to find. So in projectile motion, the x velocity is a constant, so I'm just writing it as c. And the y velocity is going to be some constant minus gt, right? Okay, so now so checking these two, you can never generate the equation of a circle because there will always be a factor of time coming into picture. So the equation of circle should look something like this. So vx minus a is some constant, whole squared, plus vy minus b, the whole squared, equals r squared. So this is how the equation of a circle looks. So if we use this form, what this means is that the center of the circle is at a comma b and the radius is r, if I'm not wrong. Okay. So of course, as here we have the time factor coming into picture, we cannot, it is not the equation of a circle anymore. So A option is not going to be correct. Okay. So now the simpler way to do it is just to draw the graph directly. So basically this is a graph. Okay, so let's just plot it. So Vy versus Vx. So, okay, so at t equal to 0, how does a velocity vector look? So we have ux I cap and uy j cap. So this is the velocity vector. And now once we project it, we know uy starts to decrease because it's being decelerated. So the length of uy keeps decreasing and it becomes 0 at h max. And then it starts, and then the vector is on the other direction, right? So and when it hits the ground, once again the magnitude is uy. So this is how the uy variation looks like. So let's just say after some time uy comes to this point. So now if you add ux vector and uy vector, you'll get this as the new velocity vector because ux is fixed, right? So just using this logic, you can see that this is how the velocity vectors will look like with time. So it'll become horizontal here, and then it'll move like this. So if you mark the tip, it's easy to observe that it's going to be a straight line. Okay, so the hodograph in this case is just going to be a straight line. So it's going to be a straight line that looks like this, and this distance is going to be u cos theta. Okay, so it's going to be a straight line parallel to the y-axis. Okay, so this is the projectile motion case. Now let's move on. So let's move on to the next one. The next one is a wheel, the particle on a wheel rolling uniformly on a horizontal surface. Okay, so let's draw the wheel first. So it's rolling uniformly, so its speed is v and omega equals v by r, right? So if we choose a particle somewhere on the sphere, we know the trajectory of the particle is a cycloid, right? So if you guys have solved the trajectory of this particular particle, you might have come across that it is a cycloid, which, you know, kind of looks something like this. So anyways, here we are interested in the velocity, right? So we are interested in how the velocity vector changes with time. So if this is the point P, let's try to find out the resultant velocity. So first we'll add the velocity of the center, which is a constant vector pointing to the right, and its magnitude is v, right? Now on top of this, we have to add the component due to the rotation, right? So that is a component tangential to the point P at the wheel, and it also has a magnitude of v. So in this particular case, it will be a vector that looks something like this, exactly the same length as the other vector. Okay, so this is going to be the resultant vector in that particular case. Now here you can, you know, kind of use a trick to see how the velocity vector changes with time. So after some time, the particle will reach here, right? And here what is going to be the difference? So the horizontal v vector is still the same, but the r omega vector or the other v vector would have rotated by a bit. So if you think about it, as the particle moves along, covers a complete 360 degree, this vector, you know, takes different positions, right? So which means this vector v, it rotates in a circle. So let's try to draw that circle. So something like this. Okay, so this vector v is over here right now, and after some time it will be over here, and so on and so forth. So okay, so this circle is drawn to imagine how this v vector is changing. This is of course a constant, right? So we don't have to play around with it. So let's say after some time this v vector is over here. So what is the resultant? So this vector plus this vector will be this particular vector. Okay, so this is the new resultant. So let's draw a few velocity vectors. Okay, so in that case, the velocity vector will be this vector. So after some time, it will once again move to this particular point. So it is very obvious from, you know, this logic that the hodograph in this case is a circle, right? The special point that we were talking about at the start is this particular point. Okay, so this is going to be the hodograph. Okay, so yeah, basically that's it. So you just had to observe that v vector plus the r omega vector. If you try to figure out the resultant for all points, the tip traces out a circle. So okay, and equation wise, so how you would do it is write down vx as a function of this angle theta, right? So it would be some v. So if this is the tangent would make an angle theta with the horizontal. So it will be v1 plus cos theta, right? And vy is going to be negative v sine theta. So yeah, now you just have to do the tricks you learn in coordinate geometry. So if you divide with v, subtract 1, you have cos theta on the right side, and vy over v is negative sine theta. Now you square and add it. Okay, so now this is clearly a circle's equation. So essentially the vx vy relation should be an equation of a circle. So that's the main idea. So B option, yeah, the hodograph is a circle. So B option is correct. Now C option, they're talking about Brachistochrone curve. Now the thing is, they also did mention some additional detail that it's a cycloidal curve with the least time of I don't know what this is, but it has the least time of descent. Okay, I'll explain what that is. But this information itself is just enough to say that the hodograph will be a circle, because in option B, we know that this particle's trajectory is a cycloid, right? And so which means the x relation and the y relation, if you try to figure it out, so this will be some r1 plus cos theta, and y will be some r sine theta, right? If you guys have done it will be similar for option C as well if it's a cycloid, because the equation of the cycloid remains similar, right? There might be a few differences because the cycloid can be origin shifted or it can be inverted, but ultimately, as it is a cycloid, the steps remain similar. Okay, so what the brachistochrone curve is, even though it's not relevant to this question, it's basically, think of another cycloidal curve, but the idea is that if you have 2 points A and B, something like this, gravity acting downwards in this case, and if we release a bead at this particular point A, and if we try to see the time it takes for the bead to go from A to B, assuming there's no friction, and if we check that particular time out for all the curves, so let's say a straight line connecting A to B, a circle connecting A to B, a parabola, you can take all the curves, and if you do the experiments, what you would observe is that the cycloidal curve, which has the least time of descent to go from A to B, and this particular curve is just called the brachistochrone curve. You can check this out on Wikipedia. Okay, so yeah, this is kind of like a simulation. So I don't have the highlighter pen, but you guys can just see, right? So if you look at the 3 balls, the red ball reaches the other point the quickest in comparison to the other points. So yeah, the solution is kind of complicated, how you end up with a cycloidal curve. It's there on Wikipedia if you guys want to check it out. But yeah, for the current problem, it's just enough to know that it's a cycloidal curve. And with the logic that we used in the second problem, we can say that the hodograph is a circular one, right? So now coming to the elliptical orbit of a planet around the sun. So now we are talking about the elliptical case. So the sun is going to be at the focus and the particle is moving along the elliptical curve. So what will be the hodograph in this case? So once again, we need to figure out like Vx and Vy, how the functions look like, and we need to come up with a relation among that. So for figuring out Vx and Vy, we are going to use the polar representation of an ellipse. So I've already done the calculations earlier. So basically in polar coordinates, which is like using r and theta, where the origin is actually the focus of the ellipse, the equation of the ellipse takes this particular form. Okay, so I'm not going to derive it right now, but this equation is called the polar form of the equation of the ellipse. Okay, so I mean, you guys can skip this too. I don't think this is in JEE, but I just wanted to show you guys the proof. Okay, so this is the distance r, this is the angle theta, and if you vary r and theta, you can cover all the points on the ellipse. And the equation is going to be this particular one. Okay, and this constant p is this one where L is the angular momentum of the particle with respect to the origin. Now, so now as we are interested in the velocity vector, because ultimately we want to draw the hodograph, right? So we need Vy and Vx. So first we'll start with the polar coordinate definition of the velocity vector. So if you guys know this, great. Otherwise, yeah, this solution would be hard to understand. So essentially the velocity vector generally in polar coordinates is represented as r dot, which is the rate at which the magnitude r changes in the r cap direction, which is along the position vector's direction. And then another component r theta dot, which is basically r d theta by dt in the theta cap direction. Okay, and theta cap direction is that direction which increases the angle theta. So it's going to be in this direction. So, and in equation, this is how it is written. So yeah, now it's just about a lot of calculation. So first we figure out r dot, which is the time derivative of r. So all you have to do is differentiate this with respect to time, and it will look something like this. So using chain rule, once you differentiate it with respect to theta, then you differentiate theta with respect to time. This is going to be r dot, okay? And then you take this thing and plug it in over here, and you end up with this. Now we want Vx and Vy, right? So we need to once again resubstitute r cap and theta cap. So yeah, this is how r cap is represented in terms of Cartesian coordinates. So this is easy to understand because if you just take a look at r cap for this situation, this is going to be r cap. R cap is a unit vector, right? So its magnitude is 1. And this angle is theta. So this is that right triangle. This is 1. This is theta. So the x component is going to be cos theta, and the y component is going to be sin theta. Okay, so from here, we'll just say r cap is going to be cos theta I cap plus sin theta j cap. And you can do the same for theta cap. It will look something like this. Now it's all about, okay, so now we'll take r cap and theta cap, put it over here, and we end up with this equation. Okay, so now we also take the help of the fact that the angular momentum is mr square theta dot, because if you guys have studied gravitation, about the focus, the angular momentum of the particle is conserved. Okay, so now how did we get this? How did we get angular momentum as mr square omega? So about the origin, once again, the velocity of the particle is r dot in this direction and r theta dot in this direction, or r omega, right? So what is the angular momentum of this particle? It is m times v perpendicular, which is the r omega component, times r. So we have m times r theta dot times r. So this is how we got mr squared theta dot as the angular momentum. Okay, so from here, theta dot can be written as L over mr squared. And now it's just a bunch of calculations. You guys can check it out if you want. But finally, you get the velocity vector. Once you have this, okay, so this thing is going to be a constant. So, and from here, it's easy to see that Vx is some constant sine theta. Vy is some constant cos theta plus another constant. And this is basically just an equation of a circle, right? If you take the k to the other side, divide it with c square and add, it's going to be the equation of a circle. So the hodograph in this case is also the equation is going to be a circle. So yeah, this is basically how it will look. So on the left, we have the elliptical orbit, and on the right, we have the hodograph. Okay, so yeah, that's the solution to the problem. So it's going to be BCD. This is the problem number 2. So here we have a smooth ring, and it's located in a vertical plane. So there is a small ball. The ball is in a position of equilibrium, which is over here. It's given a horizontal velocity such that it breaks away from the trough at a certain point. It falls onto the trough at the starting point. Okay. So yeah, this is a pretty calculative question if you are going to do it from scratch. The steps are pretty standard. So first we'll mark the point. So let's say it breaks contact at this point, and right before breaking contact, its velocity vector will be tangential to the circular path. And if this is the center of the circle, the acceleration vector will be towards the center at this instant, and it would be v square by r, right? The centripetal acceleration. There will be tangential, but I'm not marking that. And the only force at this instant acting on the body will be mg, okay, because the contact is now broken. So let's just consider some angles for this point P. So if this is point P, and if I say this angle is theta, and this would be theta as well. So it's obvious that v square by r is going to be equal to g cos theta, right? Mg cos theta is providing mv square by r. So from here, v squared equals r g cos theta. So if the velocity at any point is rg cos theta, it's going to break contact at that point. Okay, so this is, let's say, the first equation. Now we can relate v and u pretty easily using one energy expression. So just find out the height difference between these 2 points. So that would be r cos theta and add r to it. So r1 plus cos theta. So we can say u square is going to be v square plus 2gh, and h is r1 plus cos theta. And v square itself is rg cos theta. So this would be rg 2 plus 3 cos theta. Okay, so this is how u square is related to theta. Okay, so now the next part is that the particle will move along a parabola, and after some time it will meet the original location. So like if you guys have checked out the solution, they have directly mentioned that 3 theta, I guess they took this as is equal to 180. Okay, and they directly wrote theta as 60. Okay, that's because they are using a result which so if let's say the projectile were to hit some other point, let's say this particular point, and if this particular angle was some alpha, so there's a relation between this alpha and theta. So alpha is pi minus 3 theta. Okay, so there is some. So once you solve the complicated equations, you get this relation between alpha and theta. And if the parabola hits the origin, then of course alpha is 0 in that case. So if you put alpha equals 0, you will get what they wrote in the solution booklet. Okay, so yeah, I'll show you how that result is derived. So yeah, now the steps are pretty easy, right? So you have a projectile motion. So let's just say the point P is the origin for the projectile. So this is, I'm saying, the y-axis. This is the x-axis. V vector will make an angle theta with the x-axis, right? So yeah, now you know the x displacement. So now with respect to this origin, which is the point P, we can figure out we know the coordinate of this point, right? It's going to be r sine theta. I'm considering the left direction to be positive x, and negative r 1 plus cos theta is the y coordinate. So now you just have to plug this into the trajectory equation. Okay, so the equation of trajectory, which is y equals x tan theta minus half gx squared over u square cos square theta. So here of course it won't be here of course instead of u it will be v. Yeah, so to this particular equation just substitute the coordinates of this point and substitute v square as well. You get a trigonometric equation which if you solve you'll get the answer. But I'll just show the calculation for the general case which I was talking about, which is the angle alpha. So yeah, once again the calculations are a bit annoying. So the steps remain the same. So we know that v square is rg cos theta, and figure out the x and y coordinate of point P. It will look something like this. Okay, and then you plug it into the equation of trajectory. You guys can check this out, but there's a lot of trigonometry going on. And finally, once you solve that equation, you get alpha equals pi minus 3 theta. And then another solution which is like physically meaningless. Of course, mathematically this is true, certainly, but like physics wise it doesn't make sense. So you can take some example for theta. So let's just say theta is 45 degrees. Okay, so if you put 45 degrees into this equation, you get 180 minus 135, which is going to be 45. So this is a physically possible answer. But if you put theta equals 45 into this equation, it'll be 45 minus 180. And like if you add 2 pi to it, it's going to be like, it's not going to change anything. Okay, so the answer we got here was 45 minus 180 minus 135. So this is how we define positive alpha. So negative 135 would be somewhere over here. So of course a particle cannot come and hit this particular point. That is physically impossible. So alpha going to be, so any solution where alpha is like negative 90 or above, which represents this region, it's going to be physically impossible. So you guys can check it out for different values. So solution is physically meaningless. So the only meaningful solution for us is going to be alpha equals pi minus 3 theta. So that's a relation that alpha and theta follows. Okay, alpha is pi minus 3 theta. And here if you put, so now the thing is, for the current problem, we know the trajectory looks something like this. So in this case, the final coordinate is over here and the alpha value is going to be 0. So if you put alpha 0, you get theta as 60 degree. Okay, and this is, so basically in the solution, they directly wrote it. If you have theta, you can find V, you can find U. What else did they ask? They wanted U, they wanted V, they wanted the maximum height. So the maximum height is, so the projectile, let's say it is something like this. So the maximum height is going to be this particular point. Okay, so if this is the trajectory, you just have to find out what is this height from the ground. So that will be the height of the point P. Let's say it is HP, and to that just add the maximum height of the projectile, right? So h max of the projectile plus the y coordinate of point P will give you the maximum height. So once again, if you have V and theta, you can figure out H max. So basically the goal, if you have theta, you can find out anything. Okay. So yeah, that was basically it for this question. Now, now problem number 3. So here we have a weightless inextensible thread, which is thrown over a pulley, and it's attached to a load of mass M on a smooth horizontal surface. A boy pulls the horizontal end of the thread with a constant speed U. So U is a constant here. At some instant, the inclined surface of the thread makes an angle alpha with the horizontal. The pulley is at a height h. The dimensions of the block and the pulley can be neglected. The acceleration of gravity is g. Consider only the motion of the block before it lifts off the surface. The middle point of the string between the block and the pulley, not a fixed point on the string, is P naught. Okay, so yeah, basically this part of the string, they're saying the middle point, which is not lying on the string. So basically if this is the string, let's say, it's not the physical point which is at the middle. Okay, this point will of course move along the string. As the string is pulled to the right, you can imagine that this point will move along the string as well. But they're talking about the space point, which is like located exactly in the middle of this rope. Okay, it's not the physical point that lies on the rope. That point will also start rising. So like for example, if you mark this point as red, the point on the string, as you pull this rope, the block will shift to the right. And the rope and the new rope's position will be something like this. In this case, the red point will start moving above, right? And after some time, so this is not what they're talking about. They're talking about the point which is always the middle point. So even in this case, the point P naught is the middle point of this rope. Okay, so we'll see it. So I'll explain it once more in the next page. But what we have to find is what is the velocity of that space point P. Okay, and the next is that, and we have to talk about the tension, and we have to find the magnitude of acceleration. Okay, so we have to talk about how is the acceleration varying with time, the magnitude of it, and the normal acceleration of the block. Okay, so this is a bit weird. So like if they're talking about the acceleration along the y direction, it is of course 0, because we have been told that the block is like not breaking contact. So there's no y motion of the block. The block is only moving along x, right? So if it is the y acceleration of the block, yeah, this is 0. But okay, so we'll start with option A, which is the speed of the point P. So basically, so what point P is, look at this part of the rope, find the middle point and mark it. So let's just say this is the middle point. This is going to be the point P at this instant. So let's draw a clone of this image. So let's draw one more image, okay, where the rope advances by a bit. So the rope is pulled slightly to the right and the block moves to the right by a bit, something like this. So the block over here, it has moved to the right, and this end of the pulley and this end of the rope is pulled to the right by a bit. So okay, so let's just say the physical point on the string at this location is P dash. Okay, so P dash would have also moved along the rope in the upward direction because the rope is being pulled, right? So P dash, might have ended up somewhere over there, but P is still exactly at the midpoint. So what is the midpoint of this line? That is what P is. Okay, so yeah, as that is clear, now we can talk about the speed of that point P. So the speed of the block is given to be V, right? And let's just say after some time, the block reaches this particular point. In an infinitesimal time interval of dt, this block would move to the right by v dt, right? Okay, so now for the point P, it's going to be somewhere over here. What is the coordinate of point P? Observe that the height of point P is h by 2. So if the height of the pulley from the block is h, the point P is at a height of h by 2, right? And it is always at h by 2. So after some time, the point P is over here. So the point P is actually moving horizontally. Let's say the velocity of point P is Vp. So this particular tiny distance is going to be Vp dt at this instant. So now we can use similar triangles, I guess. So this triangle is similar to this large triangle, but it's exactly half the size, right? So So the altitude of the large one is h. The altitude of the small one is h by 2. So it's half the size. So this is a half scaled triangle of the bigger one. So this side is going to be half this side, right? So Vp is going to be half of V. So a velocity of point P is just going to be V by 2 I cap. And that is it. So option A is correct. Okay. Next is the tension in the string at a given instant. So for tension, we're going to talk about the acceleration of the block. Okay, so first things first, there's no acceleration of the block in the y direction, right? Because it's in contact with the ground. So the resultant acceleration is of course in the x direction itself. So let's just call this as A. This angle is given to be alpha. Okay, and of course the resultant velocity is also along this direction. So yeah, one way is to figure out V in terms of U, which you can easily figure out. So if this component is U, you can say V cos alpha is U, or V is U secant alpha. And from this, you can figure out the time derivative of V to figure out the acceleration. So if V is U secant alpha, dV over dt, this is once again the magnitude of acceleration. U is a constant, so it is U sec alpha tan alpha times d alpha by dt, right? So this is going to be U sin alpha over cos squared alpha. So now we just need to figure out d alpha over dt. You can use the physics logic to find d alpha by dt. So as this angle is also alpha, the component of velocity normal to this line is V sin alpha. So the omega of this line, which is also d alpha by dt, is going to be V sin alpha divided by this length, right? So let's call it as R for now. So d alpha by dt is going to be V sin alpha divided by R. Okay. So now we just need to get rid of R. So this is a known quantity H, right? So R is going to be H cosecant alpha. So this is going to be H cosecant alpha. So a sign goes to the numerator. Now let's get rid of V. So V is going to be U secant alpha or U upon cos alpha. So this is the U squared upon H cos cubed alpha. Okay, so this is just a tan cube and the others are constant. So this is the acceleration function. So we have to check if it's an increasing function or not. So as the particle moves to the right, it's easy to observe that the angle alpha is increasing, right? So if the angle alpha increases, then tan is an increasing function. So A is also going to increase. So yeah, the magnitude of acceleration will increase with time. And finally, the tension. So the tension is acting along the rope, right? So T cos alpha, the x component, is providing the acceleration. I guess they want the answer in terms of V. So we'll get rid of U. U is V cos alpha. So this is V square cos squared alpha. So this would be a cos alpha, right? So M times V squared sine cube alpha divided by H cos alpha. Okay, so this will be the final answer. And I guess there is a cos squared missing here. So this would be wrong. So yeah, that's it for this video, guys. Okay, so if you enjoy the video, do like and share the video, and I'll bring the other problems as well. So take care. Goodbye.